Hello, everyone. I'm Chris Casangino from Jane Street. I'm delighted to welcome you to this afternoon session on language design. We've got three excellent-looking talks. I'm excited to hear them. I hope you are too. The first of which will be a talk about tree borrows from Neven Villani.
Thanks for the introduction. Hello, I'm Neven. I'm here to talk about trees, about Rust, and optimizations. Here's a Rust function, write both, that takes as input two references x and y. It writes 13 to x, it writes 20 to y, and then it returns the null value of x. If we look at the type annotations of this function, we find the information that x and y are mutable references. And in Rust, a guarantee of the type system is that mutable references point to disjoint memory from each other. Therefore, when we write to y, we can be confident that the value behind x is not modified in the process. So if we know the value that is stored in x, we can propagate it through and reason that this function always returns 13. All of this is only local reasoning based on type information, so the compiler has access to all of this reasoning. And in fact, the compiler will apply this optimization and replace the load of x with a constant 13, making the function more efficient. Now remember that the correctness of this optimization relies on the disjointness of x and y. So how does that work? Well, there's a part of the Rust type checker that's called the borrow checker, whose job is to ensure that aliasing and mutability are not in conflict. That when you have a mutable reference, there are no other pointers to the same data, and that when you have references that alias with each other, you cannot mutate through any of them. That's quite a strict requirement, and sometimes it's too strict for low-level applications. For these purposes, Rust offers a mechanism called unsafe, which gives the programmer access to unchecked operations, which is effectively a way to temporarily bypass the type system. There's of course a trade-off here. If you bypass the type system, you lose the guarantees provided by the type system. So in Rust, the type system is quite strong. It provides very strong assumptions that no pointer is null. You cannot access uninitialized memory. There are no data races at compile time, you can guarantee that. If you bypass the type system using unsafe, you lose those guarantees, and it becomes your job as a programmer to enforce those manually. If you fail to uphold those guarantees, your code will trigger undefined behavior, which gives the compiler license to do whatever it wants with your code. So, how is that relevant to our specific optimization here? Here we have the same function as earlier, write both, and it's being invoked in a context where x and y, its two parameters, are created using unsafe, pointing to the same data. We are explicitly using unchecked operations to violate the assumption of disjointness of mutable references. This is observable in the return value of the function. We reasoned earlier that this function always returns 13 under assumption of disjointness, and here it is returning 20. If the compiler applies the earlier optimization, it will change the observable behavior of the program. So here we see a tension between unsafe code's ability to manipulate arbitrary memory and the compiler's desire to apply powerful optimizations. This tension is because unsafe code can break the very assumptions that optimizations rely on for correctness. The way to resolve this is to extend our notion of what UB should be. In addition to the usual causes of UB that are found in many other languages, such as null pointer, dereferencing, accessing uninitialized memory, date traces, and so on, we're going to add to Rust a new category of UB, which emerges from aliasing violations. Tree borrows is in charge of defining precisely what the aliasing rules are and when UB occurs. And what this does is it gives the compiler the license to assume that UB does not occur and therefore exploit that to apply powerful optimizations. There's a delicate balance here that must be found because the more UB we add to the language, the more powerful our assumptions, the more powerful the optimizations we can apply. But at the same time, it becomes more difficult to write code that is correct and free of UB. Some people here may find all of this pitch familiar. You may have heard of stacked borrows, perhaps. If not, it's fine, I'll explain quickly. Stacked borrows is the predecessor to tree borrows, and it has the same purpose, to enable optimizations based on aliasing assumptions by declaring that code that misbehaves with respect to those assumptions contains undefined behavior. So, in order to properly introduce tree borrows, I'll start with a brief intuition of what stack borrows does and why it's not entirely satisfactory. So here is a simplified model of stacked borrows. The starting observation of stacked borrows is that the way the borrow checker works is by enforcing a form of well-bracketedness discipline on all references in safe code. Stacked borrows extends this discipline also to unsafe code. So here is an inline version of the program for earlier, where we have an explicit violation of an important aliasing assumption. So we're going to check that stack borrows finds UB here, as we want. A new allocation will result in the creation of a new stack, with the root pointer of the allocation as the bottom of the stack. And the main rule of stack borrows is that to create a pointer from an existing one, you must first ensure that the existing pointer is at the top of the stack, and then you can push the new pointer above. So to create x from PTR, you check that PTR is the top of the stack, and you push x. To create y from PTR, here we find that PTR is not the top of the stack, so we pop until it is, and then we can push y. At the next step, if we try to use x while it is not in the stack, according to the rules of stack borrows, that's a cause for UB. So, just like we wanted, stack borrows here finds UB, the corresponding optimization is enabled. That's great. Stack borrows was implemented in the MIRI interpreter, which is the official tool for detecting UB in Rust, and has been involved in detecting many bugs, including in the standard library. But stack borrows is not perfect. First of all, many people find that stack borrows rules are unintuitive and that its error messages are hard to diagnose. That's not great when we need to write code that is free of UB. Secondly, there are a number of key features of the Rust borrow checker that are not implemented by stack borrows, not modeled. And also, stack borrows is way too strict. To give some concrete number to that, we've analyzed the 30,000 most popular Rust libraries, and we identified over 6,000 individual test cases where stack borrows finds UB. That's a few too much. That makes stack borrow the leading cause of UB in the Rust ecosystem. It means that the model of UB that stack borrows defines is, in some sense, not well aligned with people's intuition of what it should be. So what we want for tree borrows is a model that is overall more permissive, while retaining as much of the optimization potential of stack borrows as possible. We find it is possible to have such a model, provided that we replace the stack at the core of stack borrows with a tree instead. To give some sneak peek into how much more permissive we can get the model to be, more than twice as permissive. 54% of the tests that stack borrows finds contain UB are accepted by tree borrows, so we have a much more permissive model. What I'll do now is use one example of a known technical limitation of stack borrows to give you an intuition of why stack borrows is insufficient and how moving to a tree can give us a more fine-grained model. Here is a 3-element array, and stack borrows will view this as 3 independent stacks, one for each location. When we create a pointer to the first element 0, it gets added to the corresponding stack. Same thing for element 2. But the stack we're going to be most interested in is the stack at index 1. A common pattern that we find a lot in the ecosystem is that we take a raw pointer, we do some pointer arithmetic, and we use that to access into a different location of an array. If we try to do that in stack borrows, and if the corresponding pointer x0 is not in the stack at index 1, this will trigger undefined behavior. So in order to accept this code, we would need x0 to be in that stack. Now that's not the only possible scenario that could occur. What if instead we took x2 and offset it into index 1? Now UB occurs if x2 is not in the stack at index 1. So we would also need x2 in the stack at index 1. We can't tell in advance which one of these two scenarios might occur, and stack borrows forces us to choose a complete ordering of all pointers up front. What we would really like is the ability to have both pointers side by side, but we can't have that within the constraints of a stack. Already we can see some form of tree structure that emerges. So let's start over, finally, with trees. A new allocation will produce a new tree with the root pointer of the allocation as the root node of the tree. And the main rule of creating new pointers in tree borrows is that you insert them in the tree as a child of the pointer that they were created from. So x0 is a child of root, x2 is also a child of root, and finally we have the ability to represent them side by side. An additional piece of data that we're going to store in the tree is a per location permission. This tells us what are the locations that we're allowed to access with each pointer. Quite naturally, root has the permission to access the entire allocation. In this particular example, x0 has claimed access to index 0, x2 has claimed access to index 2, and the permission to index 1 is still up for grabs. No one has written to index 1 yet. We have a permission that means we have not yet decided which of these pointers is going to be granted access to this location. This choice is going to be made when we have more information. So in the first scenario, x0 accesses into index 1, we give x0 the corresponding permission, and we kill x2 at index 1, ensuring some form of uniqueness is preserved. In the opposite scenario, we do the reverse. We give x2 the permission and remove and take it away from x0. So this is an example where tree borrows is capable of accepting both scenarios. Stack borrows rejected both. So here we have a case where tree borrows is much more permissive than stack borrows. Of course, that's only useful if tree borrows is still capable of finding a necessary baseline of UB. So let's check that tree borrows is still capable of declaring code obviously misbehaving as UB. This is again the same example as earlier, where we have an obvious violation of disjointness of mutable references. And here it is through the lens of tree borrows. Root is a new allocation, PTR is a child of root, X and Y are two children of PTR, and we have not yet chosen which one of these pointers is going to be granted access to the data. When X is written to, Y loses the permission, and when we attempt to write to Y, this causes UB. Success. Tree borrows can indeed declare that this code contains undefined behavior. You may notice that compared to the case of stack borrows, here UB triggers one line later. This is an artifact of the fact that tree borrows is more permissive. It leaves the program a bit more room before it declares a violation of the aliasing rules. So I've shown an example where tree borrows is more permissive, an example where tree borrows is still capable of finding a baseline of undefined behavior when necessary. All that's left is to do a more systematic review. The first axis along which we've evaluated tree borrows is there sufficient UB that important optimizations are possible? We have formalized tree borrows in the Rocq proof assistant on top of the SimilarIris framework. And we've proven correct a number of building blocks for optimizations under the assumptions of tree borrows. In particular, the optimization that I've used as an example since the beginning, we can prove that correct in Rocq. On the other side, we must ensure that tree borrows is permissive enough that code that people naturally tend to write is allowed. I've already given away the final result of this one. Tree borrows is more than twice as permissive as stack borrows, and the number of regressions is negligible. These results have been confirmed by an independent study. A different team working on FFI found that tree borrows accepts more real-world programs that call foreign functions than stack borrows, and that this is in part due to how tree borrows handles pointer arithmetic. If you'd like to try out tree borrows for yourself, tree borrows is officially shipped with Miri, so you can either run that on your machine, or even easier, upload your code to the Rust playground and try it on there. See if your code contains undefined behavior. If you'd like to learn more about the technical details that I've skipped over, we have plenty of additional reading material, or you can ask any questions and we'll be happy to answer either right now or later. And finally, if you're interested in this kind of research, there are postdoc positions available at MPI and at ETH. Thank you for your attention.
We have plenty of time for questions. There's a microphone up front here if you want to come to the microphone to ask them.
Marissa from University of Utah. Thanks for the great talk. What's the impact on type checking speed?
Okay, so note that tree borrows is not inside the Rust type checker. It's in an external checking tool, so it does not affect the type checking at all.
So what is the impact on the stack borrow? What is the speed like?
So in Miri, tree borrows is a bit slower than stack borrows. Miri is already much slower than compiled code. It's not used for applications where speed is actually a concern. So we consider that the slowdown is not a significant downside, but there are always improvements that are possible, of course.
Hi, Sasha, Imperial College. Do you have a plan for the leftover 30K tests that don't pass? How many of those you think are real undefined behavior that should not be eliminated as test failures? And how many do you think?
So you mean the 3K?
Yeah, 3K, sorry.
Yeah, so there are 6K stack borrows violations, 3K tree borrows violations. I guess I could contextualize that with how many violations of other kinds of UB there are. So stack borrows is the leading cause of UB by quite a bit, because the second one, I believe, is uninitialized memory is around 2.5K. Bad deallocation is around 3K. There's another one I forget. Help me here. That's fine. So whatever. This brings tree borrows in line with other kinds of UB where stack borrows was far more prevalent than them.
Cool, thank you.
Hi, Jakub Pachurski, University of Cambridge. I have more of a clarification question. I also see the comment in the red box.
Yeah.
And what I start wondering is, so stack borrows and tree borrows are sort of supposed to be approximations of undefined behavior, and then there's an actual point which says what is undefined behavior. So could you just put this on a spectrum and say how those three things relate? And like in terms of what is safe approximations and unsafe approximations? Because this seems to imply that this might become an unsafe approximation, and that's a bit surprising.
So stack borrows and tree borrows both try to be the defining model of aliasing UB.
Okay.
What they should be approximations of is the actual UB that is currently being exploited by the compiler.
Yeah.
There is no other model that proposes aliasing UB for Rust. So if one of stack borrows or tree borrows is stabilized, they will become the definition of UB, not an approximation of the UB.
Okay, so this is specific. So code that is accepted by tree borrows may be declared unsafe. So it's possible that this will be standardized to be stack borrows, but right now it's both are safe. Both like detect all the aliasing.
Currently, it's recommended to be compliant with stack borrows, just in case a model that's more strict than tree borrows is stabilized.
Yeah.
But stack borrows as it is basically guaranteed to never become the standard. Way too many people would complain about that.
Okay, thank you, that clarifies it. Thank you.
I think one more question while our next speaker gets set up. Dan, if you want to start. Thank you.
Sure. Jonathan Aldrich, Carnegie Mellon University, and one of the co-authors on the ICSI study that you mentioned.
Excellent.
So I just wanted to say thank you for sharing your work, which is amazing, before publication, so that we were able to build on it. I think it's a great win for open science.
Thank you.
All right, let's thank our speaker again.